So we were discussing linear transformations last time, and there is these two important theorems related to linear transformations, and they make some statements about image and kernel of the linear transformations. So what's a kernel? Kernel of a linear transformation. So if you have a linear transformation from a vector space V to a vector space W, then kernel of this transformation is the set. It's a subset of the first space V from where you are going to the other space. It's a subset of V. So all those vectors which are mapped to the zero vector in the W. You have this V over here and W here. You're doing a mapping. So there would be some subset, all of which are mapped to the zero vector, one single vector, 0. So this would be the kernel of this linear transformation. Similarly, there is image of L, and this actually you can define for a subset. So if again you have L from V to W, and you consider a subset of V, then you just look at where does this subset lands in W. So you have V, you pick yourself not a subset, this is a subspace of V. You pick a subspace of V, S, and you just see that where is this subspace mapped. So it will be mapped into some subset of W, and this subset would be the image of S in W. Let's write it L of S. So where does this set S lands under the action of this linear operator in W? So L of S is a subset in W. This lives in W. Kernel lives in V, but the image lives in W. W is LV for some V in S. So collect all those vectors which you get by transforming the vectors of this subspace S. Now, there is a very important and interesting theorem. It says, well, there are two parts, or you can consider two theorems. Kernel of L is a subspace of V. Kernel was just defined as a subset. All those vectors which are mapped to 0. It was a subset of V, but the theorem says it's actually a subspace. Similarly, the second part says that the image, or this L of S, is a subspace of W. So we started with, in this second part, we started with a subspace in V, but where it lands in W, we were not guaranteed that it would be a subspace. It's just some subset of W, but the theorem says that where it lands also forms a space, a subspace of W. So how do you prove it? Proof of one. Well, first of all, we can notice that kernel of L is not empty because we proved last time that the zero in V, it does belong to the kernel of L. Why? Because we proved that under the linear transformation, any linear transformation, the zero has to map to the zero of the other space. So at least zero is there. Zero is part of kernel always. But what if there are others? Well, then you notice if V1 and V2 belong to the kernel, which is non-empty, then all you have to do is check if a linear combination of them also belongs in the kernel. That's enough to show that it's a subspace. So then, if I make a arbitrary linear combination of these two and check what happens, so all you are using is linearity of this operator, of this transformation L. Now, since LV1 is in the kernel, so this is 0. And LV2, V2 is also in the kernel, so LV2 is the 0. So this is just the 0. So that shows this also belongs to kernel. But that's enough to show that the kernel is a vector space, hence a subspace of W. Similarly, part 2 is easy. Again, L of S is non-empty. Well, it has to be non-empty because it's just you have a mapping, so it goes somewhere. L of S contains 0 of the second space. Why is that? Because S is a subspace, and any subspace, because a space always has the 0 vector, contains this 0 of V. And L of 0 of V is 0 of W, so that is contained in the L of S. Now, you can again check for W1 and W2 in L of S. If I consider A W1 plus B W2, I have, if W1 and W2 are in L of S, that would mean W1 comes from some V1 and W2 comes from some V2 where V1 and V2 are in that subset S. So this linear combination is then of this form. But now I can use the linearity in reverse, and this has to be equal to this. So that means this vector, and here this thing, because we started with the subspace, V1 and V2 were in the subspace, that means this combination is in S. Then this, because it's saying that this vector comes from applying the linear transformation on a vector of S. So this vector AW1 plus BW2 belongs to L of S. Hence, L of S is a subspace W. Let's see its example. Projection. If I define, I'm just considering from R2 to R2, and I'm defining this linear transformation. So what it does, if you have any vector, it retains only it projects this vector to x-axis because it kills its y component. If you have any other vector, it will be projected like this. So it's a linear transformation, and let's find what is its kernel. So you have to find all x, y such that they land to 0, 0. But this, we know that x, y already lands to x, 0. So this will happen if and only if x is 0. So that means these vectors for any y are in the kernel. So kernel is all vectors of this form. Y arbitrary. So in other words, all vectors along the y-axis, they are in the kernel because they are all projected down to, when you project them down to this 0. And as we by now are well aware that vectors along a line, they form a subspace. It's a one-dimensional subspace. So it's a subspace. And what is the range of this? So range, I can consider the range for any subspace. Let's consider the range for the whole space, R2. That's also subspace, improper subspace, but a subspace. So this is just x0, the x-axis, and it's a subspace. I can take another example. Let's consider P4 to P4, the derivative operator. We are considering polynomials of this form, where A, B, C, D are arbitrary numbers, and we're considering the derivative operator as a linear operator because derivatives are linear. We have discussed it last time. So what's the kernel? Kernel of D. So when I apply it to an arbitrary polynomial, I get 3ax squared plus 2bx plus cx. And I want this to be 0. So it will be 0, x square, etc. that keep separate, you don't give them value. It will be 0 if and only if a, b, and c are 0. That means all polynomials, all these numbers, 3, 4, 1, all polynomials which don't have x or x squared, x cubed, they fall in the kernel. So kernel of D is just the real numbers, real line, which is a one-dimensional subspace. While if I look at the range, and again, range I'm computing for the whole space. I could do it for a subspace, but I'm just doing it for the whole space. I get these numbers, but since A and B and C are arbitrary, well, it wasn't X, it was C. They're arbitrary, so I can rename them. And A dash, B dash, and C are still completely arbitrary. So it means that the range of P4 is P3. So you get a three-dimensional subspace. Now let's move to the matrix representations. We did some examples. So let's first a little reminder. We had that if we have a linear transformation from Rm to Rn, then I can make my vectors over here, these m component vectors, and represent this linear transformation by a matrix. It is m by n. So it acts on these n component columns from Rn, and this matrix acts and gives me m. And this matrix does the job of L. And we saw that how to construct this matrix. So this matrix was just constructed by taking the standard basis of R of Rn of Rm, because you're acting on M and going to N. So you get, well, you are acting on M components and constructing an N component. So I wrote it the other way, like this. So each, you're living in, you start with the basis of Rm. You have M basis elements because it's an M-dimensional space. You start acting with L. You construct some vector in Rn. So each one of this vector which you put in here has M n rows. So this matrix is n by m. This is how you just make it. We can generalize this to any vector space and any basis. Generalize to L from any V to W, because we know that all of these vector spaces, we can pretty much map them into Rn's. So there's not much, whatever you can do in Rn and Rm, you can do in any vector space. So any Vn and any basis E of V, let's say V is n-dimensional and W is m-dimensional. And these are the bases. Then we know we can write the vectors in V as linear combination of this basis. Similarly, vectors in W can be written as linear combinations, some other linear combinations of the basis of the W. So you're given some basis E and F for these two spaces V and W. Given these bases, you can construct a matrix which does the job of L, a matrix which represents this linear transformation. And the matrix you get depends on what basis you choose. You change the basis, you get a different basis. So this matrix you get is with respect to a basis. Its shape takes the form depending on what basis you choose. So how can you find this basis? So let's consider, let me write it like C. So let's take this arbitrary vector V in, this goes from 1 to n, and this goes from 1 to m, V, and apply my linear transformation. So because of linearity, this linear transformation will just go hit the basis elements. This is what we discussed last time. If you know the action of the linear transformation on the basis vectors, you literally know everything about the linear transformation. So this action of the linear transformation which change this basis vector and put it into the space W. And I'm calling that vector as dash. Important to note that these vectors vi dash are in W. They're not in V. So they are in W, so I can expand them in the W basis. For each Vi dash, I will have these coefficients aj, and because I have an index I over here, so I label them with an I as well. Like this. Now I can change the order. Ci, Wj. I can write it like this. Now, what do I have over here? I have these Wj and its coefficients. So this L of V is a matrix, is a column in the space W. So if I look at its representation or its column vector in this basis W. So we had defined these things, which we called the components of a vector in a basis. We can collect them in these like this. These are the components of LV over here. And this equation is saying that they are given by this thing. And this is nothing except the matrix multiplication of this matrix A, whose rows are these J and I, whose components are AJI, and this is acting on this column made up of C's. But this is nothing. Ci's are the vector representation of V in the basis in the given basis. I had given it a name E. In basis, this was in basis F. And if you look at this matrix, because this is just the matrix product of AJI with CI, of this matrix made up of AJIs, what are these AJIs? AJI are, let me put it up so that you can see. AJI are just made up of, you take your, you transform your basis vector of the vector space V. Those give you these Vi dash. And then you expand them in terms of your basis in W. So whatever columns you get, you collect them in your matrix. That forms this matrix A. So you let's do it with an example. So how to form the matrix A? First, how to form A? Apply L on V's and expand them in basis W, in basis F of W. Collect these column vectors in a matrix. This is the matrix of linear transformation. So let's see it with an example. So suppose you have this one, and the basis in R3, you are taking it to be the standard basis. And basis in R2, you're not taking it to be standard. You're taking it to be B1, B2, where B1 is 1, 1, and B2 is minus 1, 1. And the linear transformation which you are given is this. It takes any V, and V has components V1, V2, V3. Maps it to this vector in R2. And what we want to do is find the matrix of A. Matrix A representing L with respect to these bases. So you do this, apply the linear transformation. That was the recipe which we discovered in the previous over here. So you act, and this gives you 1 times B1 plus 0 times B2. So its matrix, its vector representing in this basis is just V1, 0. Gives you 0 times B1 plus 1 times B2. So its representation is 0, 1. One B2. So this is also 0, 1. Therefore, the matrix would be 0, 1. And what's the job of this matrix? We have done it before, but let me just do again. So if I'm given this matrix, it tells me where does it land. Now, given this vector from R3, so I get 1, 0, 0, 0, 2, minus 3. So it gives me minus 1. But this is not its representation in the standard basis. This I know, I should know that this I'm writing as minus B2, and B1 was just 1 1 minus minus 1 1. So this is 2 0. So if I look in the standard basis, it's actually the vector 2 0. But I had constructed this matrix directly relative to the new basis. So I got the answer in the new basis. This was its components in the new basis, which was not standard. And let me do another example. So consider a linear transformation from R2 to R2, and it takes a vector x1, x2. Now, if I want to construct its matrix in the standard basis, relative to standard basis, that's easy. I know I just do this, and since they are already expressed in the standard basis, I just didn't do anything. So the matrix is 0, this one. Matrix of L relative to standard basis. Now, if instead we choose, if we use basis this one, then all I have to do is use my procedure, apply the linear transformations on these bases, these new basis elements. How can I apply? I can just use, because this is the basis elements expressed in the standard basis. So I can use this matrix A, which I just constructed. It tells me how to transform any vector. So I can apply it on to these new basis vectors, and I will know that where will they end, where will they land. So I get 2, 1 plus 1, 2. And the second basis element goes to -2, -1 plus 1, 0. Now, if I want to get the matrix of the transformation in this new basis, relative to this new basis, I cannot use these because these are the components of the transformed vectors in the standard basis. I have to first express them in terms of the new basis. We must express these in terms of u1 and u2. So in other words, I have to expand these in u1 and u2 and pick up the coefficients. But now let's bring in what we did a few lectures back. We know that if we do this change of basis, from an arbitrary basis to the standard basis, that can be done through this matrix U. So if you're given a vector represented in a basis U1, U2, you multiply it with this matrix U, you will get its representation in the standard basis. And this is just 1, 1 minus 1, 1. But to go back, we want to go in the reverse direction. We are given the components in the standard basis and we want to find the components in U1, U2 basis. To go back or to do this, going from this basis to U1, U2 basis, you use the inverse, which if I compute for this matrix, it turns out to be this one. Therefore, if I need to just, I have got these vectors, I apply U inverse. So this is just, how did I get out these vectors? By applying A onto the component, the vector of U in the standard basis. I applied A, with A was the transformation matrix of the linear transformation in the standard basis. Then I apply U inverse. To express the components of the transformed basis vector into the new basis. So I get 1 plus 1, 2 minus 0. So it's nothing fancy. What really happened was that you had this vector 1, 1. Let me just do this, all this in a simple way. You had this vector 1, 1. Our rule told us what to do. Multiply the first component by 2 and then add the two components. So the rule told us to get this. And if I had to express it in the new basis, this 2 multiplied with the first vector of the basis already gives me whatever I wanted in this. So these are the two coefficients, 2, 0, which I collect to represent it in the new basis. So that's all that has happened, but I have done it in a fancy way over here. So let's do it in the fancy way for the second basis vector as well. So that's what I have to do. It's fancy right now, but when you're dealing with many components and arbitrary kind of transformations, it comes much more handier to do it in a systematic way. So the second basis vector had landed onto this -2, 0, and then I just express it into the new basis using this change of basis matrix. And then I have to just collect these. So this B is just 2, 0, minus 1, 1. This matrix is supposed to now do the transformation directly in the new basis. Because now you have L of U1 is 2U1 plus 0 U2, and L of U2 is minus 1 U1 plus 1 of U2. You can write it like this. But if you look at the columns of this B, what are these? These were just U inverse A U1, and this was just U inverse A U2. So B U2 but what was this matrix? U1 U2. This was just U, the change of basis matrix in going from this basis U1 U2 to the standard basis. So that means this matrix B is nothing except AU. Where, for clarity, let me write B is the matrix representation of L with respect to U1, U2. A is the matrix representation of L with respect to this other basis, the standard basis, and U is the matrix of transformation from this basis to the standard basis. So you can write this discussion into a theorem. If you are given the basis for a vector space V with two given bases, and S being the transformation matrix that takes you from F to E, and A being the matrix representation with respect to basis E of a linear transformation L. B, the matrix representation of the same linear transformation with respect to the other basis, F would be so this form is called a similarity transformation. If a matrix B is equal to, for some S, then B is said to be similar to A. And you can note if B is similar to A, then A is also similar to B. Because you can multiply with S from the left, and then S inverse from the right. This gives you A is equal to, so there is a matrix S inverse which relates B to A in the same way. So two matrices A and B which are related like this. There is a matrix S and you multiply from the left with an S inverse and from the right with an S, or the other way around. If any such matrix exists, then you say that A and B are similar. So why is it similarity important? Because if A and B are matrix representations of a linear operator, in two different bases, then we have just seen above that then A and B must be similar. That's what we have seen above. And it works the other way as well. If A and B are similar, so if A is equal to S inverse or B is equal to S inverse AS, and you are given a basis for V, आपके पास कोई basis है V1, V2, Vn, which has the matrix A as its matrix representation, as the matrix representation of L. You have given a linear transformation, you're given an A, and you're given an A, so that means it's given in some basis. You get a matrix representing a linear transformation only when you have a basis. So then you're given another matrix B, which is similar to it. What can you say about this matrix? Well, you say that I can use S to transform the basis. You can imagine applying S inverse on these basis vectors, whatever components you get, you write V as A1 V1 plus A2 V2 so this is the column representation of your vector in this basis. You apply S inverse, you will get a new column. And this will be, when you apply S inverse, your vectors will remain. Then you can apply these on your basis vectors. You'll get new n vectors and they will be linearly independent. Why will they be linearly independent? Because S has an inverse. S inverse is invertible. So we have learned it that if I apply this kind of invertible matrix, then the new vectors which I will get will still be linearly independent. So they will be a new basis for me. I have n vectors which are linearly independent, so there will be a new basis. And if you just apply S inverse on the components of your any vector, you will get the representation in the new basis. So that means this B will be a matrix representation of the same operator, but in a new basis. So the idea is that if you are given, if you are living in an n component space, and if you are given an n by n matrix, then we know that this can represent an operator on the space. It's a linear operator, it's a linear transformation on your space. But this operator, this matrix, it may get different forms depending on what basis you are using. It's not just one fixed matrix which represents this operator with this abstract operator. You have this V, and this A maps different vectors to different points, to different other vectors. Let's say this is L, this operator. With this L, you will have a matrix. Or other way around, because we saw it last time as well, that if you just give me a matrix, that defines an operator. But this can take very different forms. If I transform it in this way and get a new matrix, this matrix would be, in a sense, describing the same operator, just in a different basis. So the similar matrices represent same linear operators expressed in different bases. Matrices related by similarity transformation represent same operators expressed in different bases. Of course, if you are told, if you're given two matrices which are different and you're told that they are written in the same basis, then they are not same, then they are different. But arbitrarily, if you are given two matrices and you're just told that these are two operators, then you should suspect that if they are related by similarity transformation, maybe it's the same thing expressed in different bases. So let's do an example. So suppose you're given this, you have a linear operator from R3 to R3. That means you can represent it by a 3 by 3 matrix, and it's defined through this matrix. So this is this matrix in the standard basis. In standard basis. And suppose you want to find A in this new basis. So when I apply, remember what I need to do. I need to apply the linear transformation on these new basis vectors. And whatever I get, I have to express it in terms of the new basis. Its representation in the new basis. So when I do LV1, 1 minus 1, 0, I get 2 minus 2, that gives me a 0, and 1 minus 1 plus 0 gives me a 0, and then 3 uh, minus 1, 0. Wait, let me change it a little. Let's put a 1 here. So 1 minus 1, 0 will give me a 0. So its representation in the new basis as well would be 0, 0, 0. When I act on this guy, I get minus 4 plus 2. So I get minus 2, minus 2 plus 1 plus 2. So gives me 1, and minus 2 plus 1 plus 2 gives me a 1. So this is just the y2 vector. So the expression is easy. And when I do y3, I get 2 plus 2, 4, then 1 plus 1 plus 2, 4, and then again 4. So this is again easy. It's the 4 times the y3 vector. Uh, this way. So its matrix would be just collection of these. And since it's the matrix of the same transformation in the new basis, in a different basis, so I know that there has to be some S so that this is true. And I know what actually I know what S is. S is just the matrix which transforms the basis. And that's just the collection of the U's, the Y's. So even before doing this computation, I know that these D and S, D and A are related. This matrix is S inverse times 2, 1, 1, 2, 1, 1, 0, 2, 2 times 1 minus 1, 0. Let me just write 2 S. So this kind of thing becomes handy in many applications. If you are given the matrix of a representation and it's complicated like this, sometimes you can find a new basis where it will look much simpler. Like over here, this is a diagonal matrix. So then your job would be to find an S. Finding an S is finding a change of basis or finding a new basis where your matrix of linear transformation takes a simpler form. For example, it could be upper diagonal, or like for example, it could be diagonal matrix. We will see that for a huge class of linear transformations, you can always bring them into the diagonal form using some similarity transformation. Um, you can also view this S, because S is constructed out of U1, U2, U3 as some kind of linear transformation. So change of basis itself can be thought of linear transformation. But what it is just the identity. You take your U1, U2, U3, do not transform them, and then express them in the standard basis. They would be just these vectors because they are already expressed in the standard basis. So if you collect them, this is then, S is then, according to our rules, the matrix of linear transformation in the new basis. But this was just the identity matrix. I didn't do anything. So in this way, you can see the change of basis also, as you're not changing any of your vectors, you're just changing the basis, and see the change of basis matrix as a matrix of the identity linear transformation. I hope we will next time, or as we move along, we will see many applications of these linear transformations. They are obviously extremely important in linear algebra and solving equations. So as we go along, we will see the applications of these concepts. Let's stop here.